Alright, welcome back. Now that it is working, we have some technical difficulties getting started. Today is Wednesday, April 15th. Another round of finals review. We're on unit, what is it, 3, 4, 4 now? Our units at least, not the College Board units. We'll continue to do a couple more review sessions, and then we'll have some actual things that you guys will do. I don't want to just have every single day be lecture. This is kind of getting a little too much, too heavy. But for now, we will cover all the units, at least all the units that are going to be on the AP test, or potentially could be on the AP test. Afterwards, we'll assign some work and other things. And then before our final, which is in June, we will kind of review the things that were not covered by the AP. Now we left off with a question, with a dynamics question. If you remember, it was this skateboard question which had two blocks of different masses, and there was a force of tension or a rope that's pulling the top block, but there's enough friction to where the entire system moves forward, or accelerates forward, I should say, together without slipping. Right, and you were supposed to let's see, you're supposed to write comments, or put the answers in the comments below. I'm not sure if you actually did. Let's see, finals review 4. Did anyone actually put comments? No comments. Oh man, so sad. Well, that didn't work. Usually the YouTubers just say, write your comments below, blah blah blah, and then they get all sorts of comments down below. Well, no comments this time, but that's all right. We'll get them next time. Maybe we just didn't know how to actually solve it. Could be. You're supposed to use FBDs and figure out the relationship between each force. So if I do I did my FBD, next step is my sigma equations. Of course, F1 sigma Fy1 is Fn1 minus M1g is equal to 0. And so Fn1 is equal to M1g, right? In the x-axis for the first block, we have, there we go, Fx1. In the x-axis, we have Ft pulling us to the right, and the force Fb, whatever that is, that's the frictional force between the blocks. It is equal to mass 1 times the acceleration. When you write sigma equations, it's for the individual masses, so the right side of the equation has the individual mass m1, unless you do an equation for the whole system. Alright, so we got that much. Let's see, here in sigma Fy2, we have the normal force N2 up. This is the normal force felt here at the base. So Fn2 is here. Fn2 at the bottom of block 2, minus Fn1 minus M2g is equal to 0. But we know what Fn1 is. Fn1 is M1g. So we could say that the normal force experienced by block 2 is equal to M1 plus M2g. So substitute. And isolate. Substitute and isolate. In the x-axis, sigma fx2, we have the friction force FB, minus the other friction force, Fs. And those are the only forces we have on block number 2 in the x-axis, and is equal to m2a. Alright, so we should have everything we need. Is there anyone in chat? We're losing. Uh-oh, our numbers are dwindling. Chat, did anyone solve this? Yesterday? We're not getting our responses. Can you guys hear me? Can you hear me? Maybe it's just the just streams are not effective, I guess. What are your other teachers doing? Are they streaming too, or doing conferences every day? Maybe it's just lecture is getting too much. Who knows? Okay, so tension is FB plus M1A, and we know A is positive, so FT is greater than FB. They can't all be equal. If they're all equal, then nothing would move, right? So we know that the right side is winning, otherwise it would not accelerate towards the right. So since A is positive, we're adding a positive term to FB, therefore FT is greater than FB. Interesting. Same thing here. FB is equal to Fs into A. All right. There you go. Greater. FT to FB to Fs. Alright, so that was the end of dynamics. Today our goal is to talk about UCM. Yeah. We'll have to, I guess I'll just have to figure out different ways to do things. If this video stuff is not effective, then we'll just do other things, I guess. I mean, different teachers are looking at projects and other things that you're just working on and then submitting. It could be like a report. Research report. Yeah, let's do a research report. I don't know. We definitely got, we have 50% of what we normally get, and what we normally get is already 50%, so 25%, yay. Uniform circular motion. Okay, recall that the actual speed is constant. So as you're going around a circle, your velocity vector is tangent to the circle. Oops. Okay. And based on how far away you are from the center, you can figure out your centripetal acceleration, which is equal to v squared over r. Okay. And AC is nice and constant as well, as long as v is constant. Now with rotational dynamics, we can actually have alpha, which is angular acceleration. When you accelerate angularly, then the tangential velocity is not constant. And when the tangential velocity is not constant, the centripetal acceleration is not constant. But in UCM, where you're not angularly accelerating, AC is constant. So alpha is 0. Okay, recall things like v equals omega. So this tangential velocity is equal to r times omega. Omega is measured in radians per second, which is equal to 2 pi over t, which is equal to 2 pi f, the frequency, in rad per second. And radian is not really a unit, remember, it's a percentage. Centripetal acceleration is an acceleration, so it's in meters per second squared. Recall that you don't have to go in a full circle to have centripetal acceleration. You can have partial circles, and for partial moments, you can say that it has a value of v squared over r. So what I mean by that is if you have a road and you're just driving somewhere on the 101 freeway, after you pass like Hollywood, there's this huge dip. Whoa. And you can pretend like this is a part of a circle. These are oscillating circles for our multivariable calculus students, where you can find the curvature, or say that the point here, down here, is the bottom arc of a circle. And so for this moment, we are in UCM, based on how fast you're going. Whoa. Right. So you can have partials. Furthermore, in 2D kinematics, 2D projectiles, so if you shoot something at an angle, remember we can use range equation and all that good stuff. It's a nice parabola. Okay, so for this parabola you can have an oscillating circle, meaning here at the apex, could be seen as the apex, or as a tangent point to a circle. Well, this circle is not very good. There we go. Of radius r. Okay. And the reason why we can say that at the top of the parabola we're at UCM is because the velocity, even though it started off at an angle, the velocity in the y-axis starts to shrink, but the velocity in the x-axis remains the same, and therefore at the top you just have an x velocity that goes to the right. That's your net velocity, You're going the slowest, but you're not going zero. Only the y component is zero. However, the force vector is straight towards the center of the circle. And since it points towards the center, we can say that for a 2D projectile at the top, we are at UCM. Only at that instant point, at that instant moment in time when we reach the apex. Consider playing Apex Legends. No, don't. It sucks. Where's Jacob? I'm sure he's lurking and getting his points. Alright, what can we do with UCM? Well, we can start, doing loop-de-loops. So if I have a roller coaster, whoa, and I want to make sure my roller coaster cart does not fall. So recall that there's a minimum velocity, V minimum, required to negotiate this loop without falling. If I did my FPD, we can see that normal force minus mg is equal to mv squared over r, so that's the centripetal force. And of course the minimum velocity happens when normal force is 0. And we get this thing, mg is equal to mv squared over r, and v is equal to square root gur. Root gur. And so that was the minimum velocity that we need to negotiate this loop-de-loop without falling off. Right. This is the same thing with orbitals or orbits. If you have planet Earth here. Oops, not very good. Let's use ink to shape. Of some radius r, and we want to orbit around safely without falling. Recall Newton's big giant cannon demo, where you have to shoot it so fast that it is going fast enough to continuously fall forever. Right. So if I did an FPD on an object that is orbiting, here's Earth, satellite here, and let's do an FPD. There's only one force that is pulling us towards the center of the Earth, and that's the force of gravity, big G. Yeah. Recall Newton's law of gravitational, universal gravitation. F capital G is equal to G m1 m2 over r squared, where this is also m times little g, where little g is the acceleration due to gravity, and that's equal to capital G times the mass of the planet divided by the radius of the planet squared. So that's surface gravity. Now we'll put a little star here. Star because the gravity that you experience is not based on the radius of the planet. It's based on how far you are from the center. I'll call this R star. Okay. So yes, gravity changes based on how far away you are from the center. Of course, when you're on the surface, you are radius of the planet away. But when you're a satellite orbiting around, you're much farther away. If we say that this is the altitude h, then r star is equal to the radius of the planet plus the altitude h, how far off the ground you are, or how high up into the skies. Oh yes. So if I know that the net force, which is g times the mass of the planet times mass of the satellite divided by how far the satellite is squared, is the only force pulling me towards the center of the Earth, we can set that equal to the, using Newton's second law, we can set that equal to Mach, or MAC, mv squared over r, centripetal acceleration. And then we get to, the orbital velocity equation, VORB. This mass here is the thing that is moving in a circle, so that's the satellite. Satellite cancels. And what we have is gm over r, where m is the mass of the planet, not the satellite. The speed of the satellite is independent of the mass of the satellite. It only depends on what it is orbiting around. And which r is this? This is technically r star. This is also r star. One of the r stars cancels. Okay. All right. Now, if we go too slow, remember you will crash back in to the Earth. If you go too fast or slightly faster, you will have elliptical orbits. Okay. And if you go even faster, you will eventually leave orbit. That's called the escape velocity, VESC. All right, now let's take a look at an AP style question. So it's something that could potentially be on a test or something in the future. It says 4 planets have been circling a star. Actually, I'm just going to pull it up on screen. I have it here. I don't want to write it. PowerPoint. Boom. Here it is. 4 planets have been found circling the star HD 4307. This was provided by the College Board. Astronomers have made sufficient observations to establish each planet's radius of orbit r and period of orbit t. Capital T is period. One of the astronomers wishes to use the data to determine the mass of the star. Okay, so we have 4 planetary data. Each planet's orbital period, and then the chart has you do r cubed and r t squared, which is leading into something called Kepler's laws. It says, suppose that t is the orbital period of one of the planets, v is the planet's orbital speed, r is the planet's orbital radius, m is the planet's mass, and capital M is the mass of the star. Using these symbols, write an equation relating v, r, m, and m. Okay, so how are all of this stuff related? So if I go back to our solar system model, so if I have a star of capital M, there are 4 planets of different radii. One's 1.2, and the other's like 2-ish, 2.8-ish, 3-ish. Okay, so here's the first one. That's not very good. Let's use ink to shape. Ah. Ooh. that didn't work. Okay, maybe it's not registering because it's highlighter. Okay, it's getting lopsided, but whatever. 4 planets, there we go. Now, what is common about each planet? Well, if it's a solar system model, assuming my circles were nice and centered, we'll just ignore the left side. There we go, now it's centered. Assuming that it's orbiting the same star here, and it's nice in circular orbits, the other forces are negligible. Okay. Every single net force vector points towards the center of the circle, which is the center of the star. Man, this is... There we go. And so if this is little m1 here, and then we have second planet m2. M2 also points towards, so the net force also points towards the center. We can say that sigma F1 for the first planet is G, mass of the star, mass of the planet, over radius of the planet squared, is equal to mass of the planet, velocity of the planet squared over the radius of the planet. Right? Oops. Where are we? Gravitation. There we go. So the force is equal to the gravitational force, universal gravitational force, and the result is a circular orbit. Therefore, it must equal Mach MAC. MAC is mv squared over r. And from there we can relate them by solving for v. That's what part A is saying. So sometimes the College Board might ask the question very weird, but all it's saying is give me an equation that relates the velocity of the planet with the radius and the masses. So if I just use the universal gravitational formula, or just VORB, the force between the planets themselves considered negligible. Yeah. Yes. Yeah, so when you're using UCM, in order for the planets to even move in a circular orbit, right, your net force vector has to be just the gravitational. So as we know, when you have multiple planets, of course each planet is going to tug on themselves, and depending on where they are on their orbit, the force vectors will be at different angles. Then you have to do components. This is far beyond the scope of AP Physics 1. But in reality, if you were to build a universe yourself, a physics engine, these problems, these multi-body problems are very complex. Some of them don't, the n-body problem does not have a solution set yet. What you could do is use a program and then solve it one iteration, one frame at a time. So you calculate all the force vectors, the net force on each object, and then let it accelerate for one small amount of time frame, and then figure out what the new position is, and then from the new position you recalibrate and recalculate the net force on each object all over again, and then do it one step at a time. One could call it frame by frame video analysis. But we're not going to do that for a solar system. So yeah, we'll just say it is negligible. So by solving for v, the velocity of each planet, it must be equal to capital G m of the star divided by how far away it is from that star. Right? So that's it. Now v is related to r. Now I have to use their variables. So v is related by capital G, capital M over capital R. So make sure you use variables given. Use variables given. So this would be the correct. This is incorrect. In part 2, let's take a look at part 2. In part 2, we want to relate. Oh, you guys didn't see anything. Oh my gosh, I forgot to switch the screen. So GMM over r squared is equal to mach mv squared over r, and then it's the Vorb equation. The Vorb equation relates the velocity, the masses, and the radius. Of course, the mass of the individual planet is cancelled out. All right, let's take a look at part B. In part B, or part 2, we are relating the period, the radius, and the two masses. So I need an equation that relates period, radius, and the two masses. Right? So, of course, Vorb is equal to square root GM over r, but Vorb is the tangential velocity for your UCM. So whatever velocity this second planet is going at is also the tangent velocity. And when you're going in a circle, think about all of the experiences from our UCM unit. If you did your 3-ring binder, you can just take a look at the UCM activities. UCM Fun Day. And when we had our car going on our circle, we were able to figure out the velocity of that car. Velocity, simply put, when you're going in a circle, is the distance over time. The distance you're traveling is the circumference, 2 pi r. And the time it takes is the period. The time it takes to complete a revolution. Right? That's it. I mean, here it is. So this V equation relates our period, our period and our radius. So by setting them equal to each other, let's see, square root of g m over r must equal 2 pi r over t. We get to the Kepler proportion. Let's go and square both. You get g, mass of the star, over the distance, radius, is equal to 4 pi squared r squared over t squared, and if I do this, let's take the t to the other side, so t squared is equal to 4 pi squared over capital G m r cubed. All right, so now we have an equation that relates T, R, M, and M. All right, let's keep going. The astronomer determines that the plot of T squared versus R cubed would result in a linear fit of the data. Ooh, how did he determine that? Well, before we do the problem, based on what you found, how can you determine that if I were to graph T squared and R cubed, hint, 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 take a look at what we arrived here. T squared versus R cubed, I get a straight line, a linear relationship. Okay, so whenever you get these types of equations, okay, think about what a linear equation means. So the linear equation is, y is equal to slope times x plus b, mx plus b. This is slope-intercept form. So m is your slope. This is your y-intercept. Sometimes we just set the y-intercept to 0 to simplify it, so y is just equal to m times x. Okay? We could use this model. So even though our variables are squares and cubes, we can linearize it by changing our axes. So our axes will represent the variables. So here we have y in the left side. So y is essentially t squared now. Whatever's in front, the stuff that is in front of our r cubed must be the slope. Huh. Looks like we have one. Hello. Did the stream crash, or is it still working? Oh, it's still working? Okay, good. Yeah, for some reason my Streamlabs says 0 viewers. I was like, whoa, what happened? Streamlabs is not working. It's buffering a lot for me. I've had to refresh a few times. Ooh, interesting. Let me take a look at my dropped frames. I didn't drop. Oh, I dropped a little bit. No, my frame is pretty steady. So, yeah, I don't think it's my connection, because I have a steady 3500 kilobits per second bit rate, and it did not drop anything. Okay, but the Streamlabs thing is not. Yeah, the viewer count is just wrong. The viewer count disappeared. All right, going back. So that means that my independent variable r cubed is my x. So let me use a different color. I'll use purple. So x is the r cubed. So if I were to graph y and x, and I get a linear line, whoa, the slope here is m. I can do the same thing by graphing t squared versus r cubed. Oh, we have a question. So that means 4 pi squared g over m is a constant. Yeah, take a look. Number 4 is a constant. Pi is also a constant. It's irrational, but it's still a constant. Oh, my pi is. Let's try it. Oh, look at this pi. Oh. Alright. My pi is also a constant. Capital G is a constant. What is capital G? Capital G is the universal gravitational constant. And capital G is 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. Right? Universal gravitational constant. And what is m? What is m? M is capital M, which is the mass of the sun or the star. And for all planets in the solar system, every single planet has the same central object. Therefore, it's the same mass for all of them. And that is why 4 pi squared over gm is a constant. And going back to the problem, so now, the astronomer determines that the plot of t squared versus r cubed would result in a linear fit of the data, right? So, I mean, on an AP test, you might just rephrase this altogether. Or it could be like, explain why t squared versus r cubed is a linear function. So you would have to conclude, first you would have to figure this out, use VORB, you set it equal to 2 pi r over t, get the equation for t and r, and once you put it in this format, this final format, then you can conclude that based on this format, this shows that t squared versus r cubed, t squared as a function of r cubed is linear because the number in front, the slope, is constant. Okay. Fill in the remaining columns of the data table. Yeah, that's pretty easy. All right. Create a plot of t squared versus r cubed on the grid below. Be sure to put an appropriate scale on each axis. Draw the best fit line. So blah blah blah. So you would you would plot all of your data, right? So on the y-axis you have t squared, and on the x-axis, remember it's y versus x. That's how we label our graphs. It's whatever we have in the y-axis versus x-axis. A bunch of other streamers have 0 viewers too right now. Bubble Guy, that is a very good observation. Unfortunately, I am concerned that you had that observation. It tells me that you are watching other streamers. Exposed! But anyway, thank you for... They're having an outage right now. Well, as long as you guys can see it, viewer count, I mean, the actual number doesn't really mean anything. It just, what it really means is, I was trying to research. Very good, Bubble Guy. What it means is it's more for my sake, you know. When I see that there are higher numbers, then that means more of my students are here and they are paying attention and learning. Because I still want you to, you know, get 5s on this AP test. All right, so my y-axis is t squared, my x-axis is r cubed. Chat, question, what are the units for the y-axis and the x-axis? What are the units for the y-axis and the x-axis? Well, the y-axis is t squared, that's period. So my y-axis would be in seconds squared. Yes. Whereas the x-axis would be meters cubed. Very good. Okay, so when you have this equation, you have to use SI units. Okay, capital G is in Newton meter squared over kilogram squared. M, which is the mass of the sun, is in kilograms. Okay, so you take your data, you start plotting it, so you should get a line. We're starting from 0, 0. So, boom. So you get some sort of line. All right. So we plotted, okay. After you plot, using your best fit line, predict the orbital period of a 5th planet that is found to have an orbital radius of blah, blah, blah. So now that we have an actual equation, t squared, as a function of r cubed, we can plug in any r. So basically, if I were to write this, this is t squared as a function of r cubed is equal to 4 pi squared over capital G, capital M, r cubed. Maybe this is confusing. This is supposed to be function notation. Actually, I'll just not write it that way. I'll just keep it in this format. So I can plug in any... Why? Oh my god. There we go. I can plug in any r and figure out what the t should be. So t is equal to the square root of 4 pi squared capital G capital M times r cubed. So that's just plug and chug. Ah, you can't see it. Boom, there it is. Yeah, I'm switching back and forth way too much and I can't pay attention. I wish you could see both screens. Right. So we took our equation, we solved for t, and then you just plug and chug. Using your best fit line, determine the mass of the star the planet's orbit around. Ooh. Ah, wait a minute. I misspoke. If I go back, we're supposed to use the best fit line to predict it, not the equation. Sorry. So in part D, you're supposed to use the best fit line, because we don't know what capital M is. Wouldn't the 4 pi squared over GM be the slope of the best fit line? Yeah. So, however, you got to be careful. That is a true statement. But when the question says use the best fit line to predict, so what you're doing, if you take a look, what you're doing is you go to your graph, right? You're supposed to get some points. You get 4 planetary data, so you should have 4 dots in your scatter plot. Boom, 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 boom. And then you use a straight edge, like your ID card, and you draw a best fit line, like so. Okay, so the best fit line may not technically touch all the points. And then this thing says use the best fit line to predict. So a fifth planet that has a radius of, what was the radius? The radius is 1.5. Now if I take a look at the planetary data that was given, the other planets are 1.2, 1.98, 2.83, and 3.71. So 1.5 is between the first and second planets, right? So if I go to my planet solar system, so we are somewhere in here, and we're saying there's this fifth planet, planet X, that we don't know about. There's all these conspiracy videos on YouTube about there's other planet that comes around every now and then. It's so silly. Alright, so that means if I go to my graph now, sorry, if it's in between planet 1 and 2, if I go to my graph, so after plotting the data, planet X should be somewhere in between. So I take a look at my best fit line, somewhere at 1.5 e, what is it, 10 meters. The t squared value will be here. And then once you find the t squared value, you have to take the square root of this to find the actual t. Oh wait, this is cubed. There we go. Whew, close. Made a mistake there. It was close. This is 1.5 e 10 meters cubed. So you find where this is cubed, and then voila. You find the t5 squared value. This is period of the fifth planet squared, and then you can square root it. Or the other option, instead of doing this, the other option would be similar to what Emma was alluding to. You can find the slope of the trend line, and to find the slope of the trend line, remember, you want to use points from the trend line, not the actual data points. So these pink points that you see are the actual data points. Okay, you want to use new points. So let's say this one here and this one here. These 2 points kind of encompass the entire data set. So this will be 0.1, this would be 0.2. Then use slope formula to find the slope. And once you find the slope, then you can solve for t that way as well. Alright, so that's how you'd use the best fit line. Using your best fit line, determine the mass of the star. So set the slope equal to 4 pi squared over gm, and then solve for m. M is equal to, do the old switcheroo, 4 pi squared over g times the slope. Alright, pretty easy. Alright, now there's no part F. What is part F? Yep. Well, almost. So I'm going to add a part F so that it's more like to be on the more like to be sorry, what am I saying? I'm going to add a part F so that it's more similar to AP style. Part F, what should part F be? Dang it, I had it. I just lost it. Yes. This part F would be, what are the limitations in a concise paragraph length response what are the sources of error for this approximation? Okay. So we went through this whole calculation, right? If you take a look at the problem, we started off with 4 planets that are orbiting a star. We know how far they are. We know what their period is, and we use the period and distance of each planet. We created a solar system model, and then we plotted all the data points, right? And we used that data point to essentially figure out what the mass of the star is. So now you have to think, what are the sources of error? Think about all the assumptions we had to make to get to this mass value. What are the limitations and what assumptions did we have to make? What are the sources of error for this approximation? Go ahead and answer in the comments below. Yeah, this time make sure you answer in the comments below in the YouTube video. All right, thanks for watching. I'll see you next time.